Okay, good morning. So today we continue to talk about the electromagnetic circuit. So before we are talking about this example, that has very brief, right, revision on the electromagnetic circuit. It says that for any coils, if you apply the currents, then there is magnetic field produced inside the coils. So to describe the relationship between the currents, the coils turn numbers, and the flux produced inside the coils, we introduce a so-called magnetic circuit. Look here, so for any coils with current that produce magnetic field, we can draw a magnetic circuit like this. Here we have a magnetic circuit source. Okay, with the source, it is supplied to a magnetic load. On the circuit, we have so-called flux. So here is the magnetomotive force. So which is the F? This is the reluctance. Okay. Then, so it says that the flux equal to the magnetomotive force over reluctance. Okay, so this is the keywords, right? This is a simple magnetic field, right? Circuit, magnetic field circuit, which involves three components. One is the magnetomotive force, F. The second one is the reluctance, S. The third one is the flux, phi. The relationship between these three is phi equal to F over S, where the phi very similar to the current and F very similar to electromotive force, the voltage, and S very similar to the resistance in a DC circuit. Okay, then so this is all the laws applicable to the DC circuit is applicable to it. That is, the magnetomotive force, where you have two magnetomotive force in parallel, okay, just like voltage in parallel. So where you have two flux branch in parallel, this similar to that current in parallel or in series. So the reluctance, okay, in series reluctance, parallel reluctance, okay, they're similar to the resistance. You can use in the Kirchhoff voltage law, Kirchhoff current law, and even the network resistant network laws to applicable to the phi, F, and S respectively. Then, so when you're looking into the details of the coils, we have if you have a coils, that coils has turn numbers N, and the current go through the coils is I. Then the magnetomotive force F equal to N times I. Okay. Then the reluctance. reluctance related to the core materials and the coil's length. Generally, the longer of the coilus, the bigger of the reluctance. And permeabilities, mu. Cross-sectional area of the coilus path. Here, once again, the L is the equivalent magnetic flux path length, and A is the equivalent cross-sectional area of the magnetic flux path. Mu here refers to the permeabilities of the magnetic core materials. And furthermore, the phi has been related to the magnetic density B and cross-sectional area A. Okay, and any parts of the circuit, if you know the flux there, you know the cross-sectional area A there, you can estimate the flux density B here. Okay. Now, so the relationship between to describe the magnetic force applied, okay, magnetomotive force applied to the coilus, we introduce a magnetic flux intensity. Okay, so for a typical coilus, if it is a complicated one, be careful. That is the okay, and we introduce magnetic field density related to the magnetizing strength. That is the mu H. Okay. So generally, if you know the values B and the values H, then the permeabilities mu can be found, okay, by using the B, okay, over H. And to link to the electric circuit, we introduce a flux linkage to a coilus. That's the coilus turn numbers times the phi, the turn. Okay. So, which further can be related to the inductance. Okay. So, because the names note telling you there is an inductance caused by this inductance. Okay. So first, physically, we have a coilus that to the coilus we apply a current I. The turn numbers of a coilus is N. Then the coil has an equivalent magnetomotive force F. Okay, F. Then, so the coil itself has the cross-sectional area A, has a effective magnetic flux path L. It has a core materials. That core material has permeabilities mu. Then we can define, okay, so the magnetomotive force F, that is products of 10 numbers of currents. We can define the reluctance S, that is related to the length of the coils L, the core materials permeability mu, and the cross-sectional area path A, like this. Then the flux, total flux in the coils can be estimated using the phi equal to F or S. So furthermore, that the flux density inside the coils times the cross-sectional area of the coils, that is the total flux, which is easy to understand. And we also have so-called magnetizing force, okay, strength, or we say magnetic field strength, okay, or magnetic field, okay, strength, which actually is the magnetomotive force, okay, that average over the length of the coils. Okay, so this is the physical meanings in practice, because in practice it is very difficult to get exact length of the coils of the path. Imagine, okay, if you have a coil in the air and the coil is shaped in a straight line, so but it is limited, so it is difficult to get the length of it. Okay, and then the magnetic density and magnetizing force, okay, this magnetizing force H, their relationship linked by the so-called mu, okay, permeabilities. These are permeabilities. Okay, so therefore, in practice, by doing experiments to get the relationship between the B and H. So you look at here, the B, it is the B determining the phi, it is the phi determining the big phi, and it is the big phi determining the inductions. The induction. So the induction is the voltage. On the other side, look at H. The H actually depends on the strength of the current. Okay, H depends on the strength of the currents. Okay, so the current bigger, H bigger. But current bigger does not mean B bigger, because the depends on the mu, right? If the mu very small, the B is small. Mu bigger, B is bigger. So in practice, for a given coils, you can apply different values of the currents. So you have different values of H. And on the other side, you can measure the induced voltage across the coils. When the current change, the induced voltage change. This induced voltage proportional to the inductance, which represents the strength, okay, of the magnetic density B. Okay, because the phi, okay, big phi, this big phi is in phi, that is the B. Okay, so this, okay, proportional to the B, and this proportional to I. Okay, so in practice, you can use the oscilloscope to, okay, observe, okay, the current applied to a coils and the voltage across the coils. Their relationship will be BH curve. I think here I give you clear concepts on the BH curve experiments. Okay. Okay, so with this in mind, okay, remember what I wrote here is this, right? That looking at these questions, we try our best to understanding each of the meanings, okay, of the parameters given here. So once again, consider again the example 1, which is air-cooled, right, toroidal coils, which is a ring coils. Okay, so example 1, it is okay, plastic ring. So we calculate the inductance, flux density, and relative permeabilities. If the core is cast steel having the following BH curves, BH characteristics. Okay, so what does it mean? This is the magnetic core, which has different permeabilities at different level of H. Okay, so I just explained to you what does it mean by the H. H is the magnetizing force strength. Okay, so which has a unit of the turns amperes per meter. Look at here, amperes per meter. Okay, turn has non-unit, ampere per meter. Okay, so the turns ampere per meter given here. Look at here. Okay, that is the that B is the Tesla, which is the strength, density, magnetic field density, okay, which is density related to the flux related to magnetic strength. Okay, so as I just explained, in practice, you can monitor the voltage against the current that you got to the BH curve. Okay, so for given materials, when you have H 0.25 ampere per meter, of here is kilo, right? Kilo. That is 250. Okay, so ampere per meter, 250 meter. Then you have 0.17 Tesla, and so on. So when the H increases to 500 ampere per meter, then you have the flux density 0.54 Tesla. And when you have, right, so when the H increases to 1 and the flux density increased to 1.0.2 and so on. Look at here, the relation between the B and H is non-linearly. Okay. So because B equal to mu over times H, so the B H mu their relationship. So here ask you to estimate the BH characteristics plot the permeabilities versus the H, okay, and also for different, right, because this is different H, different B, so you different permeabilities, Mu R here is the relative permeabilities, referred to the mu 0. Okay. Mu 0 is this free space permeability, which is 4 pi times 10 minus 7 per Henry, per meter. Okay, so it is easy to get, right, the mu R over the H, because the B over H, that is mu. Then mu over mu 0, that's mu R, right? So easy to get it. Okay. And the second one is that calculate the flux density in a core for a current of 5 amperes and 10 amperes. Okay. So for different currents, that flux density will be different. And also the magnetizing force strength H will be different. Okay. They will have different flux density. Okay, they therefore have different energy densities. Okay. So furthermore, what will be the inductance of the coils if the applied DC voltage is the same as that calculated in the example 1? So in example 1, you calculate that the coils has a resistance 1.37 ohms. Okay, if you apply voltage that you calculated in the example 1, so you got the current there. How much is it? Are you still remember? Then 5 amperes. You got 0.7 volts, then 5 amperes. So with that amperes, 5 amperes, that here the inductance will be different. Previous inductance that is very small, very small. But for this coil it should be very larger than that. That's it. Anyway, so all the key here is that BH is a nonlinear relationship, real ampere. That's making that you cannot got analytical solutions between the B and H. Okay, so the key is that for magnetic materials, that the mu equal to B over H, it is no longer a constant. So making the calculation slightly complicated, because when you change the current, the H changed, the B will change, and the mu also change. So making that the calculations with the laws, we say the magnetic laws here, slightly different because that the mu here is changed. For each step with different I, you have determined the mu. Therefore, you have determined the reluctance F. S. For the different F, reluctance will be different. That the phi will be different. While in the DC circuit, for different voltage, the resistance keeps no change. The current can be easily calculated. So here, this is the difference. So making that, so making that the reluctance changes with mu, mu changes with H changes with the current. So mu changes with the current, S changes with the current. When F changes the currents, S also change, the phi also change. That's the difference. Okay, so with this slide in your mind, we go ahead to see that we with this circuit in your mind, it is easy to find out the solutions about the inductance, flux densities, relative permeabilities, and the energy densities. Okay, so now we are with the previous slide in your mind. Good. Okay, so based on the given values, pH curves, we can draw a pH curve in diagrams like this. This can be easily achieved by using the Excel, right? If you have the tables, table values, you can do it. Okay, so for example, showing here, you can see, Basically, look at here, for values from below, it is almost a straight line. For this part is almost a straight line. But with values bigger than this one, is nonlinear one. Okay. look at here. So from this curve, you look at that, and when the current is small and a small current, so the pH curve is a linear one. Okay, and a small current, pH curve is a linear one. But larger current, pH curve is nonlinear one. Therefore, for small current, you can consider a constant permeability mu. For large current, be careful that the mu changes significantly with the currents. Okay. For small current, one can consider a constant for large current. Okay, so I write down some things here so to recall somebody's memories. For small current, one can consider a constant permeabilities because at a small current, it is a pH curve is a linear relationship. So B over H will be a constant, right? Okay, believe some students still will be confused, right? Okay, after lectures. Okay, for large current, the permeability changes with the current significantly. So be careful. When the current becomes bigger, so they will change significantly. Okay. For this case, okay, for the current equal to 5 amperes, okay, for current equal to 5 amperes, okay, one can estimate about the H values. Okay, so the H values for the coilus, you still remember the coilus? So which is toroidal coilus. We can return to the previous examples to see the coilus. This coilus. So this coilus, example 1, it has average length. This is the this is average length L. Okay, average length. So this is length L. Using this L, not using this one. Okay. Using this one. Okay. Okay. So using the pi times 155. This is 500 turns. This is 5 amperes. Okay, example 1. Okay, this is okay. So this L is the pi times 155 millimeters. Okay. Length. Okay. So turn numbers 500, current 5 amperes. So you can got about 1,000 134 ampere per meter. This is the H. So that is the point, right? And this points, and this points. Okay. So from the pH curve, you can estimate the V values that is bigger than 1.6 Teslas. Someone may say that because the calculated values here is not in the tables. Okay, it's not in the table. How can I do it? Please do in the interpolations. Okay, for examples, for this case, the values given, okay, for the 4,000, okay, ampere per meter turn number, okay, ampere per meter for H, and for 6,000, okay, that is given 4,000 ampere per meter. For 4,000 ampere per meter is given. For 6,000 per meter is given. So these two values are exactly given, but your calculation is 1,133. It is between these two. So between these two, how to get the B values? Okay, for the 4,000, it is given in the tables. For 6,000, is given in the tables. So you want to find the B values corresponding to the to this one. You can use the interpolation techniques. Okay. So you can got the values from the between 4 and 6. Okay, between 4 and 6. What do you calculate? Okay, 5.134. Okay, so the value should be between these two. So you can use in the interpolation techniques to get the exact B. Okay. So I think you have no right questions on the interpolation techniques. Okay, since you all have learned the simple right mathematics during your high school. Okay, so anyway, interpolation techniques, you got the B, okay, from the BH curve, from the table, or from a simple calculations. Okay, so the BH ratio give the mu values. In this case, the permeabilities and 5 amperes can be estimated. Okay, so this is the mu values. Okay, the free space or absolute permeability is 4 pi times 10 minus 7. Okay, mu 0 is very small. Okay, remember the mu 0 is a constant. Okay, is a constant. Okay, it's constant. So this is the total mu. So you can find out relative permeabilities, okay, mu r, by using these values over these values. Here I do not do that because it's too simple, right, for your graduate school, for your college students. So then you got a mu. Once you got a mu, you got the S. You got S, you got inductance. So in the end, the inductance or toroidal coilus. This is inductance toroidal coilus. Okay. Look at here. This is mu, not mu zero. No longer be mu zero. Okay. Don't be mu zero. So in the previous example, that is the okay. In example 1, that is mu zero, but here is the mu. Okay. So you can got the inductance that is 78.59. Okay. 59 millihenries. So this H and this H different. Okay. This is Henry and this is Henry. Okay, so H here once again is the magnetic field strength, okay, or magnetizing force. Okay, the H here is the Henry. Okay, do not confuse of it. Okay, so this is the inductance. So the rationale already okay, talked about that. Okay, at the beginning of the tutorial sessions. Okay, in your mind, you have the circuit, you have the concept. Okay, so then, so you can estimate the densities. This is the energy density, as I actually already talked, okay, in the last lectures. Okay, so the BH over BH products over, okay, 2 is the energy densities. Someone may already learn from the teaching PPT, because they may have preparations, learnings. So this is energy density. Remember it? Okay, energy density. pH over 2. That's energy density. So you can also try that for different values of the currents. Okay. Okay, so that's these examples. Anyway, so remember that's the difference. And that's the difference. So continue about example 2. So we use the same coilers. Consider the toroid dimensions and the details given in example 1 and 2. What will be the flux in an air gap of 0.2 millimeters produced by a radial cut in a core? Plot the variation of the coil's inductance with the current over the range 1 to 10 amperes. Okay, 1 to 10 amperes. Then compare with the values for the complete ring core in example 1, example 2. That will be different. Example 1, you got the air-cooled coilers that has an inductance very small values, which are about 0.83 millihenries. In example 2, you just change the core materials into cast steel materials. Then you got the 78 point, something millihenries. So 0.83 millihenries and 78.9 millihenries. Big difference. The difference comes from the permeabilities. Okay. In example 1, okay. Example 1. Okay. Here we're using U to represent permeabilities. Okay, in example 1, okay, the inductance equal to the N square, okay, times permeabilities, that is mu 0. Okay, so cross-section area A over L. Okay. Example 2. Okay. L equal to N square times the mu, okay, times the A over the L. The difference is the mu 0 and mu. Okay. So the example 1, example 3, sorry. Example 3, that's different from the both, right? Ring okay. So as a result, okay, the L will be, okay, so turn numbers, okay, square over the reluctance. Okay, so the reluctance will be, okay, has different parts. Okay, so the ring core here, okay, the core plus the gap. Looking at here, example 1, it is a complete air-cooled coilus. Suppose we're using the U here for permeabilities represent. Then the inductance can be simply calculated, okay, which can be simply calculated. Still can be like this over the reluctance. Okay. And the reluctance equal to, okay, simply speaking, okay, that is the L over mu A, mu 0 A, okay. Okay. Which can still keep it right in, okay. So this is the common one, okay, that is square over the reluctance. Okay. And the reluctance equal to, okay, the length of the coils over, okay, that's the permeabilities, okay, times the cross-section area. The difference, that is 1. Okay. So S core, okay, S core equal to the length of the core over the permeabilities of the core materials at the cross-section area of it. And the S air gap, that is air, okay, which is the gap, okay, over, okay, the permeabilities mu 0. Okay. That would be different, right? Okay, so now, okay, recall your memory on the example 1, example 2. Now we come to the example 3. Okay, so in the example 3, so on the coils itself, we have a small card gap. So as a result, the inductance, reluctance of the coils comes okay, from two parts. One is the core materials, the other part is the air gap parts. So the two parts are in series, so the total reluctance is the sum of the two. So for the core materials, using the permeability mu. For the gap materials, using the permeability mu 0. So you can gauge the total, okay, permeability. Okay, sorry, total reluctance. So with the total reluctance, you can estimate the inductance. Okay, that's the questions of it. Okay, that's the comparisons. Look at here. So we have a comparison here. Okay, we have comparisons. Okay, you had better write down this one. Okay, later on you can, okay, take notes from the videos of it. Okay, so with this in mind, okay, you can find out the difference between them. Because the following calculations is just to follow the rules here. Okay, I didn't calculate, okay, specific values because that is, okay, not so important. Okay, so there we just follow, okay, what I just talked there, okay, to give you a summaries about, okay, the, okay, calculation procedures. So the air gap length in a ring, okay, in a ring that is 0.2 millimeters, which is much smaller than a core length, right? Okay. Okay. So, and the cross-section area A, so the flux in the air gap can be equal to that of the inside of the core. Okay. So the gap in reluctance can be estimated, okay, using the gap length, the, okay, free space permeabilities, cross-section area, the core reluctance, which is much longer than the air gap. So this is the core length, which we calculated in previous examples, which is pi times 155 millimeter. Okay. The air gap 0.2 millimeter, nothing. Okay, very small. So you can take it away. So you can got right. So using the permeabilities, and the current values 1 amperes, 2 amperes, 3 amperes, 4 amperes, 5 amperes, and different amperes from the BH curves, you can find out the permeabilities. Okay. Okay, so for the air gap, because mu0 is given there, so for the core materials, you from the BH curve at the various current values, you can find out the permeabilities mu. This is permeability mu. So therefore, you can estimate reluctance, magnetizing reluctance. So the total reluctance is the sum of these two. So here, for your good understanding, we just write in such a way, not break in the figures, because we would like to give you some of the general characteristics of the examples. Okay, so you have the total reluctance. Remember, for a given coil's reluctance, total reluctance, turn numbers of the magnetic force there, and the inductance. So inductance, once again, as I said, is the turn number square over the reluctance. So the reluctance 1, 2, total, break in. Now, for example 1, in comparison, for example 1, because the relative permeability 1. So this term, relative permeability, because air gap, right? So you just complete coilers, right? That is the coil's length, coil's length related. Example 2, the permeabilities depends on the B over H. So the H can be estimated based on the given current, turn numbers, and the length of the coils. So this will change in, that is, this will change in. For the example 2, because you have no air gap, you can just got this one. This be 0. Okay. So for the example 3, so for example 3, if that's this example, right? For example 3, if so the relative permeabilities mu is very big, although the air gap Lg is very small. So if the products of these two is very larger than this one, look at here. So if mu r times Lg, very larger than these values, then these values will not, that this way can be ignored. That's one. So mu r leg, be there. Then so mu r will cancel. You will got a value like this. Example 1, it is a constant, mu0 over Lc. Example 3, if the mu r, okay, Lg gap much larger than Lc. Then you got a constant, almost a constant. But this constant much larger than this one because Lc much larger than Lg. Therefore, we have a sentence, air gap increases the linearities of a magnetic circuit. We have a large but relative constant inductance. Large relative constant inductance. Okay, so example 1. So example 1, small, constant. Example 2, large, but not constant. Example 3, so the 3 coils has different properties. The example 1, it is a small values but a constant inductance. Example 2, it is very large but non-constant, which changing with current significantly. Example 3, relatively large, almost constant. Okay, it's relatively large but almost constant. So that's why our air gap, we frequently in a circuit, in a magnetic circuit, to insert an air gap to increase the linearities of a magnetic circuit. Because the linear circuit is easy to control. Nonlinear circuit is not easy to control. Okay. So that's why we have example 1, example 2, example 3 with the same ring coils. We not just to showing you how to do the calculation, but we also want to tell you some things, the usage of different type of coils. Okay, so today we stop here. Remember, submit your assignment on times, okay, referring to what we talked today also. Okay. Okay, see you right next sessions.